This video is the beginning of this playlist on Surds. Um, I think it is really important for people in high school that may be dealing with things involving swords. In the last video, focusing on high school students rather, I talked a lot about indices and logarithms, and at some point we saw some special indices, and so I was talking about sorts, and I felt it necessary to focus a bit more on sorts for people in high school. So if you are preparing for say senior secondary school certificate exam in West Africa, or GCSE, IGCSE, and all this kind of exam, SAT, and all the rest of them, you'll find this very useful. Okay, so in this first video on sorts, we'll be looking at the real number system. So the purpose of the lesson is to build a strong conceptual foundation of the real number system before introducing surds. So we need to understand what real numbers are and things like that before we begin to talk about sorts. And the learning outcome is as follows: that by the end of this lesson, students should be able to classify numbers as natural, whole, integers, rational, or irrational, then distinguish between terminating and recurring decimals, identify perfect squares, explain why square root of 2 is irrational, and understand why where sorts belong in the real number system. So that's the purpose of this first video, which is a kind of introduction to a kind of foundation we have to lay before we begin to talk about sorts. So first off, we talk about an overview of the number system. So the real number system is made up of two main groups. We have rational numbers and irrational numbers. Of course, if we want to look at it on a bigger level, okay, I'll talk through this and then I'll give a kind of overview on the worksheet. So the real number system is made up of two main groups. We have rational numbers and irrational numbers, and together they form the real number. So real numbers, irrational numbers plus irrational numbers give you real numbers. That's what that simply means. So the structure of the number system is like this. You have natural numbers being a subset of whole numbers. Whole numbers are a subset of integers. Integers are a subset of rational numbers, and rational numbers are a subset of real numbers. Irrational numbers are also contained within the real numbers. So if you're going to do a kind of broad classification, right? In fact, not just focusing on the real number system, now maybe focusing on numbers at large, right? We can look at it this way: that first of all numbers, all numbers can be seen as, so you have numbers, right? So you can see all numbers as complex, okay? All numbers are complex. That is, they can be written in the form, they can be written in the form a plus bi, okay? So even other numbers like even numbers that are not complex, say something like 3, you can write 3 as 3 plus 0i. And of course, you can have actual complex numbers like 2 plus 3i, you know. So every number can be written as a complex number. That's the essence. So numbers can be said, all numbers can be seen as complex. Then following that, then under complex numbers, we then have real numbers. Okay. We then have real numbers. But this is where the division now begins. So under real numbers now, we can then have real numbers classified as rational, rational, and irrational numbers. So for real numbers now, you can then see that here now, so the b you have here now, b is equal to 0. So any case where b is equal to 0. So in a very good example of this, like I gave the other time, a good example of this might be 3 plus 2i. But then if the, of course, sometimes you can also say 2j, if the, so when b is 0 now, you then have maybe just 3. So you can say this is a real number, or and other examples like that. Then we continue with the idea of rational numbers. So for rational numbers, you have a number that can be expressed as a ratio of two numbers, of two integers. We've not talked about integers so far, but okay, I can just give the example. So for rational numbers, you have things like maybe 3 over 2. any number you can express as one integer over another integer. That's why you talk about ratio now. 1/4 is an example of that. Even 0.2, 0.1/5 is 0.25, right? So these are examples, right? So, like I said, 3/2, 1/4, even 4 itself is 4/1. So it's a rational number, and so on and so forth. So for irrational numbers now, you cannot express them as a ratio of two integers. Numbers like numbers like square root of 2, square root of 2, you have square root of 2, you have pi, you have e, you know. These are examples of irrational numbers. Then going forward, then under rational numbers, you can then begin to talk about other kinds of things you have. So under rational numbers now, you can then have further sub-classifications, like you have what the other time we talked about the idea of whole numbers and all that. So under rational numbers, you can talk about having integers. We can break them down into, say, trying to do a good classification as much as possible. So you can classify rational numbers into maybe things like uh fractions. You can have fractions. You can have integers. Okay. So for integers now, integers are whole numbers, either positive or negative. So in this case now, you have e.g., maybe, I mean, all the integers -3. Okay, well, it continues to the left, starting from the left: -3, -2, -1, 0, 1, 2, 3. These are all integers. These are all integers. On the other hand, you have fractions. Fractions can be in form of decimal and things like that. So for instance, you have the 1/4 we had before, 3/2, 3/2 is not an integer, although 4/1 is an integer. So 4/1 doesn't fit in here, for instance. So these are examples of decimal. So you can even have decimal fractions. You can have mixed fraction, proper fraction, and all these things, and have decimal fractions. So like say you have 0.31, these are examples like that. So, and so on. So under integers now, then you can say you have things like you have whole numbers, you have whole numbers. So whole numbers are positive integers including zero. So here I'm saying that we have 0, 1, 2, 3, and so on and so forth. These are whole numbers. On the here now, you can then have maybe proper fraction, improper fraction, and all those classifications. So if I like, I think I can do that. So you can say you have uh uh proper proper maybe we can even have up to 4 classifications of fractions. Yeah. So we can say, I can think of 4. We can have proper fractions, we can have improper, improper, we can have mixed fractions, and then we can have decimal fractions. Okay, decimal fractions. So decimal. Okay, I think this is me trying to do a finicky kind of classification of numbers. So under proper fractions now, you have a decimal where the number at the top is smaller than the number below. So 2/3 is proper, for instance. 5/7 is proper, 1/2 is proper. But for improper, if you have 3/2, the bigger number is at the top, 7/5. Well, 2/1 does not qualify as an improper fraction because it is already automatically a whole number, an integer, which is also a whole number. Then you have all that like that. Then for a mixed fraction now, so if you can turn an improper fraction to a mixed fraction. So 3/2, for instance, is 1/2. So you have you have an integer part and you have a fraction part. 7 over 5 is one whole number, 2 over 5, and so on. Then for decimal now, you can convert either proper or improper or mixed fractions to decimal. For instance, 2 over 3 is like 0.67 and so on. Then 1 over 2 is 0.5. Okay, so you can have all of that going. Then coming up for whole numbers now, we can then have what we call natural numbers. Okay, so you have natural numbers. Natural numbers are normal counting numbers. So in short, if you drop zero, then you have natural numbers. So here now you just have one, two, three, and so on. And one, two, three, four, five, and so on and so forth. Four and all that. So yeah, with this we have a kind of broad classification of numbers. So you have numbers, all numbers can be seen as complex technically, because all real numbers can be written as complex numbers, actually. So the real numbers are classified into rational and irrational. Under rational, you can have integers and fractions. Fractions are whole, something over something like that. And then integers are whole numbers, either negative or positive, including zero. Then whole numbers, uh, you drop off the negative part and you have whole numbers. And then if you drop zero, you have natural numbers, and so on and so forth. So that's a kind of overview of numbers that we can have, and that's the kind of thing we're considering right here. Okay, so in 1.2, let's talk about natural numbers now. So because that's like at the base of the whole thing, natural numbers. Those are normal counting numbers, natural numbers. So it's like we are building it up. We have natural numbers like that. So let's go for this. So we have the definition. Natural numbers are counting numbers starting from one. Like I said, one, two, three, four, five, and so on. So the key properties of natural numbers: no zero, no negative numbers, and they are used for counting objects. So if I say count, you just start by saying one, two, three, and you go on like that. Then examples, you can talk about 6 books, 15 students, and the smallest natural number is one. Okay. And then we move on to whole numbers. Like I said, when you add zero to natural numbers, you have whole numbers. So whole numbers are like natural numbers plus zero. Okay, so whole numbers are natural numbers including zero. So that's 0, 1, 2, 3, 4, 5. So why zero matters? Zero represents nothing, and it's a starting point on the number line. In fact, in the history of math, there was a time there was the concept of nothing was not represent could not be represented mathematically. It wasn't represented mathematically. I think someone came up with this idea of zero. Maybe an Indian mathematician whose name I think I've forgotten now. Along the line, I'm thinking of doing a playlist on the history of mathematics. I know that maybe somebody may find that very interesting. So I hope I get to that someday soon. Then you don't have, so you see whole number is equal to, so zero represents nothing and it's a starting point on the number line, and whole number is equal to natural numbers plus zero. So the zero is so important that it's a reference point when you're dealing with, when you want to have a number line. Imagine a number line like this. So you have this number line. So you always need a reference point. So on the number line, you should have zero. So when you now move to the right, you have one, two, three, four, and so on, five, and so on and so forth. On the left, you can also have minus one, minus two, minus three, minus four, and so on and so forth. You know, so this zero now actually, is very important. It's like a reference point. So if you go to the right of zero, you have positive numbers. To the left of zero, you have negative numbers. So that's why zero is really important. And zero is not the worst number, by the way, because negative is worse than if you're talking about in terms of owing, right? If you have zero, it means you're not owing and nobody is owing you. Or if you have minus, you're owing someone. If you have plus, you have, right? So like that. So the whole numbers is natural numbers plus zero. Then we have integers, right? Integers in the definition, so integers include positive numbers, including negative numbers and zero. So integers are whole numbers, including negative. Uh, so negative integers plus zero plus positive integer is equal to. Okay, I mean, I think I'm just confusing myself right now. So whole numbers, all whole integers include positive numbers, negative numbers, and zero. So positive numbers, negative numbers, and zero. I think it's better to even say positive. Positive whole numbers, negative whole numbers, and zero will give you integers. Like -5, 0, and 8 are examples of integers. Further examples now, is -7 an integer? Of course, it's an integer, it's a negative integer. Yes, because it's a negative whole number. So integers are made up of positive whole numbers, negative whole numbers, and zero. Is 4.2 an integer? No, because that's the decimal part. Because there's a decimal part here, you cannot say it's an integer. If you look at the classification I did the other time, I had this I broke down uh rational numbers into integers and fractions. So fractions are not integers. Integers are positive, negative, and positive numbers, positive whole numbers, negative whole numbers, and zero. Those are integers. Okay. And then coming back here, 4.2 is not an integer because that's the decimal part. Then we go for rational numbers. A rational number is any number that can be written in the form a over b, where b is not equal to 0. Okay, it can be written in the form a all over b, where b is not equal to 0. I'm just adding this d to make the fractions bolder, okay, and more appealing to the eyes, if you like. So that's what I'm doing. It's not necessary to do, but I just like to do that. So you can see the a over b is bigger now. So we're dealing with rational numbers. So rational numbers. Rational. If you like, you can see it as rational numbers. So you have ratio, rational, rational numbers. So rational numbers, rational numbers are simply can be written. They can be written as a ratio of two integers. So if you can write a number as a ratio of two integers, then you see that's a rational number. So I've given the example before, like 3 over 4, integer over integer. Even decimal form too can be seen as rational. So 7 over 11, okay, minus 5 over 3, etc. So as far as you already know, integers are positive and negative whole numbers, right? Including 0. So even 0 is an integer. Here, a and b are integers. So that's what I've done there. And of course, you cannot have 0 at the bottom because that's going to make the expression undefined. Example, 1 over 2, 3 over 4, minus 5 over 8, 7. All integers are rational because 7 is 7 over 1. So all integers are rational, right? Let me look at how we can figure that out. Okay, of course, we already know all integers are rational. So that's settled already. All integers are rational. All whole numbers are integers too, right? And so on. Then we can then talk about types of rational numbers. So I talked about fractions like having 2 over 3, 5 over 8 minus 9 over 4. Then uh so fractions are rational numbers. I think I talked about that in my classification here. Fractions are rational numbers, as you can see already. And then we have different types of fractions like proper, improper, mixed, and decimal fractions. Okay, so all this. Okay, again, let me do my usual perfectionistic wahala, perfectionistic issues. I have that. So 2 over 3, 5 over 8 minus 9 over 4. So then, apart from that, another kind of fractions you can have. I just talked about fractions the other time. So another type of rational numbers you can have terminating decimals. So in this case now, imagine that you have this kind of numbers we have here. So terminating decimals, these are decimals that end like you have, okay, let me split this up. So not fractions that end, for instance, 1 over 2, you can clearly express 1 over 2 as 0.5. So, and 0.75 is 3 over 4. Then 2.125, I think that should be 4, something like it. You can express it as some kind of fraction. Okay. So these are terminating decimals. They don't recur. Then you have worked examples here. So if you can convert 0.75 to a fraction, like 0.75 is 75 over 100, and you can simplify 25 goes in 75 three times, in 100 four times. Therefore, 0.75 is rational because you can express it as a ratio of two integers. Now, we then have the idea of recurring or repeating decimals. So some decimals are repeated, right? So after some division, you now begin to have uh the same numbers or a chunk of numbers being repeated from time to time. So in this case now, you have recurring decimal, or recurring or repeating decimal. That these are decimals that repeat forever in a pattern. So examples of this would include something like 0.3333333333 forever and ever, or 0.27272727 forever and ever. So you have examples here. Imagine you want to convert 0.3333 to a fraction. So the recurring decimals can actually be converted to a fraction. That's the idea we are pushing here. So in this case, now you just say um, you want to convert 0.33 to a fraction. So you can say let x be equal to 0.3333 like that. Then you can multiply both sides by 10. So you have 10 times x, right? 10 times x. And if you multiply 0.33333 by 10, you know that you are going to get 3.333333 like that. So this is exactly what we are doing. So the answer ends up being 1 over 3. We already know 1 over 3 gives us that. So I think I want to take it over to the other side, right? We have you're looking for the fraction form of this, like we said. So x is 0.3 bar like that. That means 3 is repeated. So this is simply saying that x is equal to 0.333333333333 and so on and so forth. That's what this represents. Okay. So we want to look at we want to get the fraction that led to that. So we then have, say you have x equals 0.3 repeated like that. So first, then you want to multiply both sides by 10, right? So you have 10x equals 3.33333. Because if you multiply this by 10, you're going to get, so 10x here simply means you have 3 point, it will shift by one step. So you have 3.33333333 and so on, which is simply 3.3 bar still. Okay, that's what we have right here. So, and then the next thing we want to do is, don't forget, x started out at 0.3 bar like this. So you then have 10x equals 3 plus 0.3 bar. Okay. So, and 0.3 bar is x when we started. So 10x now is equal to 3 plus x. So that means we have 10x minus x equals 3. If you transfer this to the other side, 10x minus x equals 3. So we then have 9x is equal to 3. So if you divide both sides by 9, so that you can get x. So you have 9x over 9 equals 3 over 9. So this cancels this. So x is equal to 3 here is 1, 3 here is 3. So x is 1 over 3. So we can say that, so we can simply say that the recurring decimal 0.3 bar is equal to 1 over 3. So that's the essence of this. So I like to also do the other one that involves, so sometimes the repeated numbers can be two numbers. For instance, we talked about this 0.272727272727. Okay, let's look at that. How does that play out? We have 0.27272727. Uh, so write 0.27 bar as a fraction, okay? As a fraction. So what do we have? So we say let x be equal to 0.27 bar, okay? If that is the case, don't forget this is the same thing as 0.27272727 and so on and so forth, like that. So what you need to do here, you cannot, if you multiply by 10, it won't give you the same result because you're just going to get to 0.7 something something. So in this case now, because two numbers are repeated, you have to multiply by 100. Okay. So you through, multiply through by 100. Okay. So that means you have 100x here is equal to, so if you multiply this by 100, so it moves two steps. So you have 27.27 bar. That's 27.27272727. And don't forget what we did before. This is 100x equals 27 plus 0.27 bar. Don't forget we started out with this as x being 0.27. So we have 100x is equal to 27 plus x. So then that's like 100x minus x equals 27. So 100x minus x is 99x, and that is equal to 27. So then you divide through by 99. So we have 99x all over 99 is equal to 27 all over 99. Okay, so 99 cancels out. So we have x is equal to, here now, 9 goes here 3 times, 9 goes here 11 times. So that's 3 over 11. And that is why so you can say, so 0.27 bar is equal to 3 over 11. Okay, so that's why 3 over 11 gives you 0.27 bar. So you can always have this. So we move on to the idea of irrational numbers. So it means you can write, so first of all, you see, you can write fractions. Fractions are already rational numbers, as you can see. 2 over 3, 5 over 8. Then you can write terminating decimals like 0.5, 0.75, 2.125. You can write them as rational numbers. And then recurring or repeating decimals can also be written like that. So all of these are still qualified to be rational numbers because you can write them like as the ratio of two integers like that. But then let's look at the idea of irrational numbers. Okay, let me focus on it step by step. So irrational numbers cannot be written as a fraction, and they have non-terminating, non-recurring decimals. So if you have terminating decimals or you have recurring decimals, you can still write all of this as the ratio as fractions, right? And they are rational numbers. But for any number that cannot be written as a fraction with no non-terminating and non-recurring decimals, they are irrational. Very good examples include root 2, root 3, pi, e is 2.718, blah 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 blah, you know, and pi 2 is 3.142, and so on and so forth. So example of decimal now. Okay, well, I mean, we can demonstrate this. Let me use decimals as usual, like I always like to do. So you have decimals right here, you know. So you have root 2. Imagine that's square root 2. Okay, we don't need this s. Square root 2 is 1.414213. See, there's no repetition happening anywhere. So you just have 414213. So no repetition. Same for square root of 3. 1.73205087. So it's just going, no repetition anywhere. Then imagine pi 2. You have pi. Pi is 3.141592, no repetition. So E itself is like that, 2.718, 2818, 2846, no repetition. So these are all irrational numbers, like we've been saying. So the digits continue forever without repeating. So, and that's what makes them irrational. So if you can have repeating decimals, recurring decimal, or terminating decimal, or fractions, they are rational. But if you cannot have that, then you have irrational numbers you're dealing with. And then that takes us to the idea of perfect squares, right? Perfect squares. Imagine that, okay, I mean, a perfect square is a number obtained by squaring an integer. So, okay, I think we have something lumped up here. So we have all this, we can split them up. Okay, so these are perfect squares now. 1 is equal to 1 raised power 2. Okay. 4 is 2 raised power 2. 9 is 3 raised power 2. 16 is 4 raised power 2. 25 is 5 raised power 2. 36 is 6 raised power 2. Then why do perfect squares matter? So if a number is a perfect square, its square root is rational. Okay. So the square root of a perfect square is rational. Simple. On the other hand, if a number is not a perfect square, its square root is irrational. So for instance, 2, you know, 1 is a perfect square, so its square root is 1. 4 is a perfect square, so its square root is 2. 9 is a perfect square, so its square root is 3. 16 is a perfect square, so its square root is 4. 25 is a perfect square, so its square root is 5. 36 is a perfect square, so its square root is 6. But 2 is not a perfect square because you can't find 2 here. So that's why the square root of 2 will not be a perfect square. So that's why the square root will be irrational. So if a number is not a perfect square, its square root is irrational. Example, square root of 2, 3, 5, 7, and all that. They are not perfect squares, so their roots are irrational. Okay, so imagine trying to locate the square root of 2 on the number line. You know, I already introduced the concept of the number line previously, right? So locating the square root of 2 on the number line, step 1, you can use Pythagoras theorem. You can consider a right angle with base 1, height 1, using Pythagoras. So hypotenuse is now square root of 1 squared plus 1 squared equals root 2. So, I mean, if Trying to do that with a number line. Look at this now. Imagine that you have a number line. Or in fact, we can consider two intersecting number lines, right? So we have this number line right like this. So let's say this is the origin 0, and then this is 1, this is 2, this is 3, this is 4, 5, and so on and so forth. Whereas this is -1, -2, -3, -4, -5, and so on and so forth. Now look at this. If you look at this line segment from here to here, we have 1 unit. So can we take another number line? Say, let me use green color now. So imagine another number line passing through this place. So don't forget this is already 1, right? This is 1 here. So this is actually 1 right here. So imagine another number line going through, and then this is 0. This is to the right now. This is 1. This is 2. This is 3, and so on and so forth. And down here we have -1, -2, -3, and so on and so forth, right? Now, look at this. So you have this 0, 1, that's 1 unit. You have another 0, 1 here. Okay, you have another 0, 1 here, which is another 1 unit. So if you join this up, okay, this is a right angle clearly. So using Pythagoras theorem now, so this line now is what if we call it x, that's going to be x squared equals 1 squared. This 1 squared, 1 here plus 1 squared from Pythagoras theorem. So that means that x squared is equal to 1 plus 1. That means x squared is equal to 2. Okay? X squared, 1 plus 1 is 2. So x squared is 2. So that means x is equal to square root of 2, like this. So we then see that uh on the number line now, okay, we have square root of 2 right here. So we can remove this, and then this turns out to be root 2, like this. Okay, so that's how we can locate the square root of 2 on a number line. So with that in place, then we can continue to other things. So of course, like we said, step one, it turns out to be the hypotenuse, right? The other two sides are the adjacent sides. So you have square root of 2 there. For step 2, you can then approximate value. Square root of 2 is approximately 1.414. This lies between 1 and 2 on the number line. So as you can see, 1.414 lies between 1 and 2 on the number line. So you have 0, 1. So 1.414. Of course, using decimals like I did the other time, right? You already saw that square root of 2 is 1.414141414. So at the end of the day, 1.414 is somewhere, uh, if you're looking at it from here, so it's somewhere here. I guess I want to use a color. So 1.414, so square root of 2 is somewhere here, or it is somewhere here. It is somewhere here. Square root of 2 is somewhere there, like that. Okay. So that's how we locate the square root of 2 on the number line. So now we go on to the next thing. So the 1.414 lies between 1 and 2 on the number line. Therefore, the square root of 2 is irrational. So we can then talk about how do a classification practice. For example, 1 now. Imagine you want to classify -5. -5, of course, is an integer. It is rational because you can express -5 as -5 over 1. And it's also real because all rational numbers are real. All integers are rational and all rational numbers are real. Example 2. Imagine you want to classify 0.625. So you can convert to fraction as 0.625 is 625 over 1000. And if you divide through by, I think 25, you get 25 in 625 is 5, 25 in 1000 is 8. Therefore, it is rational and it is also real because all rational numbers are real numbers. Then example 3, imagine if you want to classify square root of 9, square root of 9 is equal to 3. So in this case now, 3 is natural, it is whole, it is integer, and it is also rational. Okay, it's all of that. So 3 is a natural number, it's a whole number, it's an integer, it is rational, and it is also a real number. So for example, 4, you want to classify root 7. Root 7 is not a perfect square, therefore it is irrational and it is real. Okay? All real numbers are rational or irrational. Okay? So all irrational numbers are real too, you know. Therefore, it is irrational and it is real. And because 7 is not a perfect square, the square root is going to give you a whole number. So you say that that is an irrational number, which is automatically real, right? So then where do sorts belong actually? So a sort is a root that cannot be simplified into a rational number. So any root that cannot be simplified into a rational number is a sort, right? So root 2 cannot be simplified into a rational number. Root 5 cannot be simplified into a rational number. Root 7 cannot be simplified into a rational number. So these are irrational numbers. So since irrational numbers are part of the real numbers, sorts belong in the irrational number subset of real numbers like that. So in fact, even numbers, even decimals like 625, imagine you can still find the square root of 6.25, right? The square root of 6.25, uh yeah, the square root of 6.25, or let me do something I can easily handle. Say 2.25. So the square root of 2.25 can still be uh 2.5, I think. Yeah. 25 times 25 is 225, I believe. Let me quickly check that. I think that's the idea. 25 times 25. So you have 25 times 25 times 25. Yeah, that's 625. Okay, it's actually 625. Okay, I think 225 is 15 times 15, right? 15 times 15. So 15 times 15. Yeah, that's 225. Great. So yeah. So this is actually 1.5. So this is 1.5. This 1.5 can still be written as 15 over 10, which is the same thing as 3 over 2. So a this is still a perfect 2.25 is a perfect square. And then you can still write it as an integer. So this one is 2.25 is still a rational square root of 2.5 is still rational, right? Because you can simplify it into a rational number. And because at the end of the day, 3 over 2 is a rational number. So even that is still okay. So root 2, root 5, root 7 cannot be simplified into a rational number. So these are irrational numbers. Since irrational numbers are part of the real numbers, sorts belong in the irrational number subset of the real numbers, as you see the classification before. So, I mean, I've done a lot. I think this video is too long for what we are introducing, but I think it's fine. So you want to try your hands on the practice problem. So for each question, classify the number as natural, whole, integer, rational, or irrational. A number may belong to more than one category, like you've seen already before. So classify 8, 0, minus 2. Yeah, 0 in particular. 0 is a whole number. 0 is an integer. Okay. But it is not a natural number because natural numbers start from 1. So 0 is whole and natural. No, 0 is the whole and integer, yeah, and so on and so forth. You want to think about all of that. Of course, 0.6 is recurring, so you can write it as a rational number. Okay, so determine whether 49 is a perfect square. Of course, 7 times 7 is 49, so it's a perfect square. So the square root is 7. Determine whether 18 is a perfect square. Of course, it is not a perfect square. Between which two integers does root 5 lie? Root 5 is 2 point something. So it lies between between 2 and 3, right? So root 5 lies between 2 and 3. Between which two integers does root 20 lie? Root 20, the perfect square before 20 is 16. The perfect square after it is 25. So that means root 20 lies between 4 and 5, whose squares are 16 and 20. Every integer is a rational number. Of course, true or false, every rational number is an integer. No. Every integer is rational, but not every rational number is an integer. Because rational numbers can also be fractions like 3 over 2, 2 over 3, and so on. Write 5 as a fraction and classify it. Of course, 5 as a fraction is 5 over 1. So it is an integer and it is a rational number. It is also a whole number. Is 3.1416 rational or irrational? Explain your answer. Well, there's no repetition, so it is actually irrational because there's no recurring decimals here. Then is this 0.10100100001 rational irrational? Yeah, it is irrational because there's no particular repetition. So if we look at 1, So 1 0 1 0 0 1. So there's no pattern, regular repetition. So place the following numbers in order from largest to smallest. Of course, we can do that. This zero. Okay, the smallest should be -5. No, the smallest should be -3, followed by -5/2, which is -2.5, followed by 0, followed by 0.5, and then 2, like that. Okay, so with this, we come to the end of this interesting video about the real number system as a precursor to learning about sorts, which are numbers that cannot, whose square root cannot be simplified into rational numbers. Let me know how helpful this is for you. And if there's something else you'd like me to try out, uh, let me know. If you have subscribed already, I must thank you very much for doing that. If you haven't subscribed, this is your time to click on subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join, which gives you access to special privileges like getting to see some videos first before others see them, or being the only one to see certain videos as members of the channel. You can get PDF copies of my notes. We can hang out together to discuss whatever interests you on my channel. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.